Chemical reactions, law of conservation of matter, and writing and balancing chemical equations. By the end of the day, you should be able to define and explain the law of conservation of mass, represent chemical reactions and the conservation of atoms using molecular models, write and balance using the lowest whole number coefficients, chemical equations from formulas, word equations, or descriptions of experiments. What is a chemical reaction? Turn to page 9 in your spiral and find some free space on the page, maybe in between the Alka-Seltzer demo and the product slide, or at the very bottom of the page, to write our definition. Notice in the animation that we have these two hydrogen molecules seen in green, and this one oxygen molecule. Now they come in and they collide, and after that collision, atoms are rearranged, and they form these new substances. This is a chemical reaction. So let's write down our definition. A chemical reaction is when atoms of one or more substances are rearranged, here's our keyword, rearranged to form new substances. What is evidence of a chemical reaction? So if we were to witness this, what is some evidence that we might see or feel or hear that a reaction is occurring? One really obvious piece of evidence would be a temperature change. Another piece of evidence would be bubbles or a gas being released or a color change. These are all pieces of evidence that a reaction has occurred. Now, how do we write this? How do we represent these chemical reactions? Well, chemists use equations to represent reactions. They spent a lot of last semester learning how to write chemical formulas for ionic, covalent, and metallic substances. So we're going to use those chemical formulas to write equations that represent what's happening in the animation you see here. Generally speaking, we have reactants that are then converted to products. On page 9 in your spiral, you'll see several boxes. On the top right-hand side, you'll see reactants, and on the bottom left-hand side, you see products. You should also see this chemical equation listed here. Now we're going to use this to help us define what reactants and products are. So let's first start with reactants. And on your page, you should see a line here on these two. Let's go ahead and fill in that box with reactants. Now, these two chemical formulas, H2 and O2, represent these models down here. What exactly are reactants? At the bottom of that box for reactants, let's go ahead and write down that they're found on the left-hand side of an equation. And by left-hand side, I'm referring to anything to the left of this arrow here. They're found on the left side, and one other important feature is that bonds and reactants must be broken. Bonds must be broken. So as I'm looking at my model here, I would need to, let me choose a different color here, in order to convert these reactants to my products over here, to these water molecules, I'd have to break this bond between the two hydrogen atoms, this bond between the two hydrogen atoms, and this bond between the two oxygen atoms before my products could be formed. So at the bottom of that box, you've written down both important pieces of information. Now we're going to fill in our definition for products. So your product, I only have one in this case. Let's go ahead and label that our product. And we're going to do opposite side here. Our products are found on the right. Again, we're referring on the right-hand side of the arrow. We're also going to write down that our products are a result of new bonds being formed. New bonds formed. So when the bonds in the hydrogen and oxygen are broken, the new bonds between hydrogen and oxygen atoms are formed. So this is a new bond here. This is a new bond there. New bond, new bond. So products found on the right, they represent new bonds being formed. Chemical reactions can be written as equations to show the reactants and products. We can use a word equation, like nitrogen monoxide plus oxygen yields nitrogen dioxide. or we can use a symbolic equation. Now we're going to focus most of our efforts on these symbolic equations that use formulas to represent our chemical species or reactive products. On the bottom right-hand side of page 9, you'll see the word coefficient. Now, in our sample or example here, our coefficients are these big numbers that we see in front. And I know you don't see one here in front of oxygen. If you don't see a number, it is the number 1. I think that's important. So for our definition for coefficient, they indicate how many of each molecule there are. So at the bottom of that box, let's go ahead and write down, this again is the last slide on page 9. For coefficient, I recommend that you put, they are the big numbers in front. So when I look at this formula here, the big red number in front is the coefficient. What exactly does a coefficient tell me? How many of this molecule must be present for this reaction to occur? So one nitrogen monoxide, let me do my colors here. I'm going to do nitrogen in blue, and I'll do oxygen in red. There is one nitrogen monoxide. Now, according to this coefficient in front, in order for this reaction to occur, I need 2 of these. So this big number in front tells me that I need to draw 2 of these nitrogen monoxides in order for this reaction to occur. So big numbers in front, and they indicate how many of each molecule there are. Flip the page in your spiral. And you'll see states of matter. This is on the right-hand side, states of matter. Now, our states of matter indicate the state of each compound. So we have a few different options. You're probably already really familiar with solid, liquid, and gas. You can go ahead and add those, S for solid, L for liquid, G for gas. And in my opinion, the most important one is AQ for aqueous. This means a substance that has been dissolved in water. Most of the chemical reactions that we observed are aqueous solutions. So something that's been dissolved in water, and then we're mixing those components together. On the left-hand side, you're going to see the term subscript. So coefficients were these big numbers in front. Subscripts are these little numbers at the bottom. So let's get rid of that bonus information. And let's circle these right here. You see these little numbers here, like the little 2, that little 2. I don't see numbers on the N or the O, so those subscripts are the number 1. Subscripts indicate how many atoms there are in each element in a molecule. So if I see a formula like NO2 and I were to draw that, that means that there is one nitrogen atom. So here's my nitrogen. And I see a little 2 as the subscript on oxygen. So when I draw that, there are 2 oxygen atoms. So big numbers in front tell me how many of this whole thing, how many molecules, and little numbers at the bottom tell me how many of each individual atom there are within one of these molecules. So if there's no subscript, it's the number 1, and I see there's 1 nitrogen there. This little 2, there's 1 there, and there are 2 there. And now we get to the good stuff, the law of conservation of mass. When a chemical reaction occurs, new compounds are created, and here's the important part. No new matter is created or destroyed. Atoms are just rearranged as they change partners to form new compounds. So at the bottom of the slide that is found on page number 10, for law of conservation of matter, I want you to write this statement here. No new matter is created or destroyed. And if you're really feeling it, you can just put atoms are just rearranged. On this visual here, I see that there is 1 carbon atom, there are 2 oxygen atoms, or 1 oxygen molecule, and on the right I see that there's 1 carbon dioxide made up of 1 carbon and 2 oxygen atoms. Now the law of conservation of matter says that I'm not creating any more carbon atoms. So I have 1 carbon atom on the left and there's 1 carbon atom on the right. for my oxygen, I see 2 oxygen atoms on the left and 2 oxygen atoms on the right. So we see that the number of atoms on both sides are equal. So this represents the number of atoms on the reactant side, and here the number of atoms on the product side. So law of conservation of matter, I'm not creating or destroying any, so all of the atoms that show up on the left show up on the right. The only difference is that now they've been rearranged. So my carbon is kind of nudged its way in between these 2 oxygen atoms. In addition, we can summarize this and say that the number of atoms on the reactant side is equal to the number of atoms on the product side. I want you to add this to your definition for the law of conservation of mass underneath the symbols that you see on this slide. And last, the mass of the reactants is equal to the mass of the products. So I see that one carbon atom has a mass of 12 grams. I went and grabbed this number from my periodic table. The mass of one oxygen atom is 16 grams, and there are 2 oxygen atoms. So I've taken that mass of 16 and I multiplied it by 2. So the mass of this oxygen molecule is 32 grams. Now after this matter is rearranged, when I take the mass of this carbon dioxide molecule, the mass of this oxygen is 16, this carbon is 12, and this oxygen is 16, to give me a grand total of 44. So if I take my numbers over here, the carbon plus the oxygen molecule, 32 plus 12, lo and behold, I get 44 grams. So because I'm not creating or destroying matter, that means that the mass before is equal to the mass after those atoms have been rearranged. So ensure that you have all the stars, that you have the definition here, and that you've added that the number of atoms are equal and that the masses are equal on both sides. Now we're moving along to page number 11 in your spiral. The simplest form of a chemical equation is a word equation. For example, potassium metal plus oxygen gas yields potassium oxide. We will rarely use this format in class, but I wanted to show you a version of this. Here, my reactants appear on the left side of the arrow, but I'm using words to describe them. This plus sign here means reacts with or and the arrow in between means produces or yields. So if you want to add your symbols and their meanings, a plus means reacts with or and. It separates 2 or more reactants or products. And an arrow means yields or produces, and it separates the reactants from the products. This double-headed arrow we won't really see in Chem 1, but it does mean that there is a reversible reaction, that it goes in both directions. Now the second form of an equation is called a skeleton equation. This shows which atoms are involved, but it doesn't tell us how many molecules are involved. So for example, this model here shows a methane molecule, which is 1 carbon and 4 hydrogen atoms. It also tells me that it reacts with oxygen gas, there it is, O2, and it produces 2 products. Here's carbon dioxide, my 1 carbon, the 2 oxygen atoms, and 1 water molecule. Here's my H, here are my H's, and there's my O there in the middle. So my skeleton equation just tells me who the reactants are and what products they're making, but what's missing is how many of each I need to show that matter is conserved. As it stands, do you see that there's 4 hydrogen atoms here? But on this side, I only have 2 hydrogen atoms. So this matter is not being conserved. Law of conservation of matter says that if there's 4 hydrogen on the left, there should be 4 hydrogen on the right. We need to fix this issue. In order to do that, we are going to write a balanced chemical equation. It shows all atoms and coefficients, remember those are the big numbers in front, to tell us how many molecules and atoms there are. Balancing ensures that the number of each atom is the same on both sides of the reaction and that it obeys the law of conservation of matter. So if I take my same equation, that skeleton equation from before, and I add the coefficients of 2 in front of the oxygen and a 2 in front of the water, now I can keep a tally. Carbon atoms on this side, I see that there's only 1 carbon atom. Hydrogen atoms, there's 1, 2, 3, 4 hydrogen atoms, and oxygen atoms, there's 1, 2, 3, 4. Now to the right of the arrow, I'm going to do the same count. Carbon, 1, hydrogen, 1, 2, 3, 4, and oxygen, 1, 2, 3, 4. Now notice that there's 1 carbon on each side, 4 hydrogen on each side, and 4 oxygen on each side. So we've conserved matter because the number of atoms are equal on both sides, and in addition, because the number of atoms are equal, the mass will be equal on both sides as well. So the mass of 1 methane and 2 oxygen atoms is equal to the mass of 1 carbon dioxide and 2 water molecules. There's a few tips that we recommend for balancing chemical equations. The first is to create a table by drawing a line under the arrow in your chemical equation. We're going to list all of the elements in the order which they appear on the reactant side. We're going to copy the list in the same order on the product side, record the number of atoms present for each element and list on both sides, and then balance. Polyatomic ions, I want you to keep them as a group. I'll show you an example in just a moment. And we're going to balance one compound at a time and rewrite the number of atoms as we go. We're going to only add coefficients and never ever change subscripts. Those are part of a chemical formula. Water is only H2O. To balance an equation, I can't change this to H2O2. That would be something completely different. This is hydrogen peroxide. It has completely different chemical and physical properties. The only thing I can do to balance an equation is to add a big number or a coefficient in front. If hydrogen and oxygen appear in more than one place, we're going to attempt to balance them last. There are several steps to follow. In this case, I'm going to show you an example a little bit later on how to do just that. And if you see a hydroxide ion on one side and water on the other, I want you to rewrite water as HOH. Again, I'll show you examples of this in just a moment. Alright, let's try the first example on page number 12 in your spiral. So our goal is to balance this equation so that it obeys the law of conservation of matter. That means that the number of iron atoms on the left side or the number of iron atoms on the reactant side are equal to the number of iron atoms on the product side. Now I'm going to do a quick visual just to make sure that we're all on the same page. I see one iron atom here. I'm going to represent it with a red iron atom. Then I see this bromine molecule. It's made up of 2 bromine atoms. I'll go with green for bromine, and I'm going to draw 2 green circles chemically bonded together. And on the product side, I have this FeBr3, so it is made up of 1 iron atom and 3 bromine atoms. So I've got 1, 2, 3. Now recall that mass must be conserved, number of atoms must be equal. 1 red, 1 red. So far so good. 2 green, 3 green. We're not quite balanced. We have broken the law of conservation of matter. So what we have to do are add coefficients. Remember, those are the big numbers in front to ensure that number of atoms are equal. So I can't just randomly change this formula to Br3 and add another bromine atom here. Recall that there's a special way that we write chemical formulas, either drop and swap or those prefixes, so I can't just randomly create my own formula. Now what I can do though is add a number in front, like say the number 2, and this means that I can draw a second bromine molecule, which increases my total number of green atoms. So I went from having 2 Br to now 4 of them. Now I'm still not equal on both sides, but I think we have something going for us. I'm going to add 1 more. Instead of having 2, I'm going to add 1 more. If I have 3 bromine molecules, that gives me 1, 2, 3, 4, 5, 6 bromine atoms. If I look on the right, I've got 3 bromine atoms. I think we have solved the problem. I'm going to draw 2 of these models here. 1, 2, 3 bromine, and let's get that iron right there in the middle. And then if I look at my bromine atoms and I count, there's 3 there, 3 there. I have 6 bromine atoms. So by adding these big numbers or coefficients in front, I have ensured that the number of green atoms on the left are equal to the number of green atoms on the right. Now by doing that, by drawing this extra FeBr3, I now have 2 reds where I only had 1 red before. So to fix that problem, I need to draw another red here and change this to the number 2. So balancing or conserving matter simply means you add coefficients in front to change the number of molecules that are reacting and the number of products that are being formed. Let's use the table method to do this just a little bit more simply and less time consuming. So let's get rid of my picture here. And the answers. And let's use the table method. The table method says draw a line underneath the arrow to separate the reactants from the products. List the reactants in the order which they appear. Fe, Br. I'm going to copy that same list on the right-hand side. Fe, Br. Now we count how many atoms of each element we have. I'm looking at my subscripts, and for iron, there's 1. For bromine, there are 2. On the product side, 1 iron, 3 bromine. I always recommend that you start at the top, compare, make sure that they're the same, and then start making your way down. I see that my bromine atoms are not balanced, so I need to multiply them by a number so that they equal the same number of atoms. In our example, I multiplied this by 3 to get 6, and multiplied this by 2 to get 6. So the number which we're multiplying by now becomes the coefficient. So this 3 gets multiplied there to get 6, and this 2 gets distributed across. Now I have 2 iron atoms. Remember in my drawing I had 2 red atoms, and now I have 2 times 3, I have 6 bromine atoms. Always start back up at the top. Now I see that the iron atoms are unbalanced, but this is an easy fix. I need 2 iron atoms, so I'm going to multiply this by 2, cross that out, 2 and 2, 6 and 6. We are balanced. My coefficients are 2 to 3 to 2. Next example.